Hello everyone and thank you for attending. Today I'm going to talk about continuous tasks and the Asynchronous Computability Theorem. This is a joint work with Sergio Rajsbaum and Ulrich Schmid. So this is the overview of what I'm going to talk today. First, I'm going to talk a bit about distributed systems, then a bit about topology, and also about the topological modeling of distributed systems. And then I'm going to go over our contributions in our paper. I will talk about continuous task, a chromatic version of the Simplicial approximation theorem, and also a complete characterization of weight-free continuous task solvability and extensions to density requirements. So, we are interested in distributed systems from an abstract point of view, and we consider only finite set of processes which can communicate using shared memory, and their failure model is crashes failure model, and we are interested in asynchronous systems. And also we are interested in some tasks such as consensus and approximate agreement. So I will talk now a bit about the communication. So in a shared memory model, processes uses a common memory object to communicate, and we use a convenient abstraction. We use the iterated immediate snapshot model for this, which means that each process has its own individual memory section in which they write, but they can read the whole memory object. So the Synchrony model is an asynchronous model in which each process runs at its own speed, and computation is organized in logical rounds, and rounds happen at different real times, and each process has its own clock, and each process works at its own speed. And we are interested also in weight freedom, which means that since up to n-1 processes are allowed to crash, then each process must be able to make progress and work independently of other processes. So what is a distributed task? Well, if to define a distributed task, we need a set of valid inputs, a set of valid outputs, and a validity condition that matches valid inputs to valid outputs, and we also need terminating condition. This means when is the right moment when a process can make a decision and stop its execution. So to put into contrast sequential problems with distributed tasks, in sequential problems we are usually interested in computing functions, and usually you have a single input and a single output, and the computability is determined by the processing capabilities, and we are interested in analyzing the algorithmic complexity, while in distributed tasks the problem is to coordinate processes to compute outputs, and the computability is limited by the communication and failure assumptions, and we are interested in the round and message complexity of distributed tasks. And we are interested in agreement tasks. Agreement tasks are tasks where processes are given input values, and they must communicate to agree on some output. So for example, we could be interested that these outputs are not too large. So for example, in consensus we are interested that they decide on a single input value, or on k-set agreement where we are interested that they decide on at most k different values. Or we could also be interested in approximate agreement where the outputs must be sufficiently close, or even we could be interested that the outputs are different, such as renaming and symmetry breaking. So why do we want to study agreement tasks? Well, because they have several practical applications, such as blockchain and also databases and so on, and also because agreement tasks are useful benchmarks for studying how strong is a distributed computing model. And we want to study agreement tasks to determine their solvability, and we want to design efficient protocols for these tasks. So now I will go up into topology. So topology is all about spaces, continuous functions, and in particular we are interested in connectivity. We are not interested in general topology. We are going to be more interested in combinatorial topology, and the idea is to construct spaces from a combinatorial definition. So I will start with simplices. Simplices are multi-dimensional triangles which are defined by a set of vertices, finite set of vertices, and a face of a simplex is simply any subset of vertices. And we can use these simplices and glue them together along common borders to form more elaborate structures which are called simplicial complexes. So here we see the formal definition of an abstract simplicial complex, which is a combinatorial construction, and it's not in principle is not tied to a geometric interpretation. We start with a vertex set, and we also have a face set, and this is enough for defining an abstract simplicial complex. And as with all mathematical objects, we also have functions, and in this case the functions are called simplicial maps. Simplicial map is simply a vertex map that preserves the structure. It means that it is a function that maps faces to faces, and it is called chromatic if it also preserves some color structure. And simplicial complexes can also be endowed with a geometric interpretation, and this is very easy to use. We simply use a finely generated spaces to have this geometric interpretation, and we will use the parse notation to refer to geometric realization of simplicial complex. So for example, on the left side we have an octahedron, which is a simplicial complex, an abstract simplicial complex, and on the right side we have a sphere, and we can think of a sphere as a geometric realization of this octahedron. Another important thing to talk about is subdivision. Subdivision is an essential operation on simplicial complexes, and basically what it does is that it refines simplicial complexes into smaller faces. So for example, here on the left we have a simplicial complex, on the middle we have a barycentric subdivision, and on the right we have a chromatic subdivision of a simplicial complex. So an interesting thing is that when we have a geometric realization of a simplicial map, then this geometric realization is a continuous function, and we want to know if the reciprocal is true also. That what does it mean? That if we have a continuous function between geometric spaces, does this gives us a simplicial map that is sufficiently similar to the function? And the answer is yes, and it's called the Simplicial Approximation Theorem, which basically tells us that if we have a continuous function between two spaces, then there is a barycentric subdivision of some simplicial complex that allows us and a simplicial map that behaves very similar to the function. So we can look at this figure, and for example the red curve is a simplicial approximation to the blue curve. So now I will talk about the topological modeling. So what is the main idea? Well, the main idea is to construct a simplicial complex from the model, and we want to do this because then this helps us express non-trivial features as topological properties. For example, agreement tasks are closely related to k-dimensional holes, and the way that we do this is we take local states to define vertices, and we take global states, and these define the maximal faces or facets. of a simplicial complex, and the indistinguishability of the system tells us how they intersect, how the faces intersect, and how they are adjacent to each other. So for example, we take the two-process weight-free shared memory case. In this example, we have two processes, a green process and a red process. So because the processes are weight-free and asynchronous, what could happen is these three possibilities. Either the green process is faster and is able to finish before the red process learns its input value, or either the red process is faster, or both are sufficiently close with each other's speed and they are able to learn each other inputs. And as you can see, in this case where both processes have similar speeds, then it is indistinguishable both for the green process and for the red process whether or not the other process was able to learn their inputs. So here is the formal definition of an input complex. For defining an input complex, we simply take the process IDs and the input values, and this gives us the vertex set, and for the faces we use the input configurations, which make these edges, for example. This is an input complex for a binary two-process task. And for output complex is essentially the same, but we are more interested about outputs rather than inputs. And in this example, we have the output complex of a consensus task, binary two-process consensus. And we also need to talk about carrier maps and validity. So a carrier map is a function that maps a simplex into a subcomplex. So for example, in this figure we map this upper lead of the octahedron is mapped to only this yellow lead. This lower lead of this ectahedron is mapped to the lower lead of the output complex. However, the intermediate faces, which are shaded in blue, are allowed to decide either the upper lead or the lower lead. And this is all we need to represent a binary three-process consensus. So now that we have specified tasks with a combinatorial topological model, then we are ready to define what is a protocol complex. So the idea is that we want to capture the evolution of a distributed system, and to do that we have a sequence of protocol complexes P0, P1 all up to Pk, one per round, in which the input complex P0, and the idea is the same, that vertices of a protocol are local views and the faces are the global states of the system. And the communication operation transforms a protocol complex into the next stage of a protocol complex. In particular, in the weight-free shared memory model in which we are interested, each communication rounds really is a chromatic subdivision. So this is an example of the weight-free shared memory model, but for three processes. At time 0, at round 0, where no process has communicated with anyone, each process is only aware of their own input value. But after one round of communication, there are all of these possibilities. Of course, it could happen that the blue process was very fast and it was able to finish its communication round without learning any of the inputs from the other processes. However, it could also happen, for example, that the red process that has this view, it could be not so fast as the blue process, and both was able to learn the input value from the blue process, but it was not able to learn the input value from the green process. and this is represented by this view. Here the red process knows the blue input value, the red input value, but it doesn't know the green input value. And if we want to compute further protocol complex, we simply take each of these triangles and we subdivide it once more. So now this can be captured perfectly by the formulation of the Asynchronous Computability Theorem, which is due to Herlihy and Schmid, which basically says that a distributed task is solvable in weight-free asynchronous shared memory if and only if there is a chromatic subdivision and a chromatic simplicial map that is preserved by the carrier map of the validity decision. So here is one example of an application of this theorem. Here we can see that binary three-process consensus is not solvable in the weight-free shared memory, and the reason why this happens is because, as we have shown before, the communication in the weight-free shared memory only subdivides the input complex, which means that it doesn't matter how many runs of communication we have, this input complex will always be homeomorphic to the sphere which is connected. And if we have any decision map, since a simplicial map induces a continuous function and the input complex is connected, then we cannot use a continuous function to disconnect the input complex, which would be required by the consensus task specification. So now we can talk about our contributions. So the asynchronous computability theorem allows us to match task solvability to simplicial maps, and at the same time the simplicial approximation theorem matches continuous function to subdivisions. And now the question is, can we directly match task solvability to continuous functions? And the answer is yes, but the continuity is not enough. So let me talk you about the following task, which is the Hourglass Task, which is simply we want to map this input complex into this output complex, and the borders should be mapped to the borders, which means that this red border should be mapped to this red border, and then this other border should be mapped to this other border, and the lower border should be mapped to the lower border, and that's it. So there actually is a simplicial map that solves the Hourglass task. We simply map the borders as stated accordingly, and we map all these yellow colored vertices, we map them into this yellow colored vertex in the middle, and that's it. There actually is a simplicial map that preserves the validity conditions. But actually we cannot solve the Hourglass task in asynchronous shared memory. And the reason is really simple. It's because if we could solve the Hourglass task, we could also solve two-set agreement. And we know that two-set agreement is impossible in asynchronous shared memory. So what is wrong? Well, the answer is quite simple. The simplicial map doesn't preserve the color structure, and any simplicial map that solves the Hourglass task will forcibly collapse part of the simplicial complex. So in order to address these problems and to elaborate appropriate conditions that allow us to specify which functions can solve these tasks, we need to add an extended coloring and a simplicial neighborhood definition, which are these. Which basically the extended coloring is allows us to choose a color set for a point, and the simplicial neighborhood is simply any interior set that is homeomorphic to a simplex. So for example, this yellow triangle is a two-dimensional simplicial neighborhood, and the red segment is a one-dimensional simplicial neighborhood. So now that we have those definitions, then we can say that a chromatic function is a continuous function, and that it has this property with respect to the colors, which means that the colors that the image and that the image and the pre-image have in common should be at least the same as the amount of generators that it needs. So for example, this function is not chromatic because it collapses this red segment into a single point. So and now we can talk about the chromatic approximation theorem. So basically we give a condition for what is a chromatic approximation. A chromatic approximation is essentially very similar to the simplicial approximation, but we require it to preserve the color structure. And the theorem is that any chromatic function has a chromatic approximation. And one thing that is worth noticing is that any chromatic simplicial map induces a chromatic function. So I will now give a brief visual sketch of the proof. Basically what we need to do is to subdivide the input complex until all simplices fall inside of a star, like is shown in the picture. A star is simply the collection of all faces that contain one point. So for example, in this case, this simplex falls inside this yellow star. Once we have this, then we simply match, we look at the color of the center of the star and we match the corresponding color of the simplex to the center of the star. So we match the yellow vertex to the yellow vertex. Next, we remove the vertices that are the same color of the center of the star, both from the input simplex and in the output complex. This allows us to reduce the dimension of both the input complex and the output complex. And we also need to take a projection because this function used to be a two-dimensional function, and now it should be reduced to a one-dimensional function. And we want to do this because then if we reduce the dimension, then we can apply induction and repeat. So here, for example, we subdivide again until everything falls inside of a star. Here, for example, this simplex falls inside this red star. This also falls inside this red star. This falls inside this green star, and so on. And once we have done this to decreasing dimensions, then we recover our maps to get a higher dimensional solution. And in the end, we join all of the subdivisions to get a global subdivision, and that gives us a solution, that gives us a chromatic approximation. So we now can speak about continuous tasks. So solvable tasks in the weight-free shared memory are exactly matched to chromatic functions, and this is the reason why we can now specify tasks with continuous chromatic functions. So our chromatic approximation theorem states that a distributed task is solvable in the weight-free shared memory if and only if there is a chromatic function that is carried by such a decision map. And one nice result is that all continuous tasks are solvable in the weight-free shared memory model. So this really tells us what are the solvable tasks in weight-free shared memory. And one extra application of this is what we call the consensus-preferent approximate agreement. So in the practical applications, consensus is not solvable and is not viable. So what we do is that we use approximate agreement to solve many of these problems. And in approximate agreement, we think that a better solution is one that has a higher proportion of exact agreement outcomes. And one advantage is that we can use chromatic functions to specify exactly what is the proportion of exact agreements that we want, and to limit the proportion of non-exact agreements. And one bonus thing is that if we know the input probability distribution, then we can also control the output probability distribution, and this is shown by the following example. So here only these tiny blue portions of the input are sent to non-exact agreement, to this output where it's 1 and 2/3. But a very large portion of it is sent to exact agreement. So this red section is sent to exact agreement, where both agree to 2/3 or where to both agree to 1/3. And the takeaway is that we can use chromatic functions to define continuous tasks, and continuous tasks characterize weight-free shared memory, which is very nice, because now we can say that weight-free shared memory solvability is essentially topological and chromatic, and also chromatic functions are the key to chromatic simplicial approximation. And a bonus thing is that we can use them to express output density requirements. And that is all. Thank you very much for your attention.